Performance of rooftop solar attachments during Hurricane Ian. A review of field observation, failure modes, and design implications. This presentation reviews how rooftop solar panel attachment systems performed during Hurricane Ian. The goal is to review peer assessment and understand what failed, why it failed, and how those lessons have shaped improvements in design, installation, and code changes after the storm. Everything presented comes from literature, field reports, and engineering investigations performed after Ian. The growing use of solar panel or PV photovoltaic systems in Florida. Solar power has become extremely common across Florida because of the abundant sunlight and increasing energy cost. Homeowners, businesses, and developers have all adopted PV or photovoltaic systems, but their placements on rooftops puts them directly in harm's way during hurricanes or extreme wind conditions. Because they sit at the highest point and are elevated off the roof, they experience some of the strongest wind effects. Hurricane Ian overview. Hurricane Ian struck Florida in 2022 with sustained winds exceeding 140 miles per hour in some regions. This was a catastrophic hurricane causing losses estimated around $112 billion. This storm specifically provides one of the most important real-world tests for the PV systems or solar panel systems in major wind events. Some systems performed well, but many suffered partial or total failures. These failures varied based on roof types, installation quality, exposure categories, and mounting methods. Because Ian struck such a large region in South Florida and caused such different types of damages, this hurricane proves to be one of the best case studies for the failure modes of solar panels. Wind behavior and aerodynamics around solar panels. When high when wind accelerates over a roof and creates high suction zones, specifically at the edges and corners of the roof, solar arrays amplify the effects of wind and uplift forces mainly because of their tilt, gap, height, and spacing. Research has shown that these aerodynamic factors significantly influence these uplift forces. This explains why panels at roof edges were consistently the most vulnerable. There are two types of PV attachment types. The two primary attachment methods are mechanically attached systems and ballasted systems. Mechanically attached systems, shown on the left, anchor directly into the structure and structural members, and generally perform better under high wind conditions because of this direct attachments to the building structure. Ballasted systems, on the other hand, shown on the right, rely on weight and friction. These systems carry frames which hold ballast blocks that add weight down on the frame so they could sit on top of the roof membrane. Under hurricane conditions, especially on smooth commercial membranes, the friction decreases, allowing sliding or rocking of the entire system. There were four different observed panel failure modes, or four main different observed panel failure modes. These included complete panel blow-offs, racking system damage, fastener failure, and ballasted system sliding. One of the most common failures observed after Ian was complete panel blow-off. This typically happened at roof corners or leading edges. These areas are areas with the highest suction and uplift forces due to the applied wind loads. Once a single panel failed, the system lost its ability to fully distribute the load, creating a cascading failure around the neighboring modules. Many racking systems also deformed under dynamic uplift loads. This is because these dynamic loads are applied in every direction, causing twisting, turning, and bending of the racking systems. Ballasted systems were specifically susceptible because even small shifts in the ballast can reduce full stability of the system. This matched previous wind tunnel findings showing that ballast displacement drastically increased failure risk. In residential systems, one of the major problems was fastener placement. Some fasteners were observed to be missing in the structural framing. Like screws were driven only into the roof sheathing and not roof framing structures, and pulled out easily under the applied uplift from the wind. Corroded hardware in coastal areas also significantly reduced capacity, contributing to widespread anchorage failures. Lastly, ballasted systems lit across commercial roofs due to friction loss caused by roof vibration and gusting. This movement damaged conduits, punctured membranes, and impacted rooftop equipment like HVAC units, and in many cases, the secondary damage cost even more than the panel replacement. Correlation factors observed. Clear patterns emerged during the study. Mechanically attached systems outperformed ballasted systems. Rooftop edges and corner zones matched ASCE 7 high pressure regions, and workmanship errors such as missing and untorqued fasteners were major contributor to the observed failures. Exposure categories also played significant roles. The location of the building relative to the water experienced higher wind loads and uplift loads on the panels than those more inland. Same goes for rooftop panel placements. Those located closer to the edge or without any wind deflection device near them experience higher loads and uplift loads compared to those which were better protected and more centered on the roof. Post-Ian code updates. Several code updates and inspection requirements were changed after Hurricane Ian and the observed failures. The Florida Building Code now requires site-specific wind design for photovoltaic systems instead of the previously used generic manufacturer value. UL 2703 code requirements were also updated to include cyclic uplift testing to better simulate hurricane conditions, where before the testing only included a single uplift force on the panel system. Now it includes loads from different directions to better design for the full system. These changes significantly improve design reliability for future installations. Jurisdictions or cities code ordinances have strengthened inspection requirements. These now include mid-installation checks to ensure anchor replacement, torquing of the fasteners, and spacing. Manufacturers have also released high wind racking system with stronger rails, corrosion-resistant hardware, and aerodynamic deflectors. The evidence shows that PV performance during hurricanes depend on design, installation, quality, and location on the roof. Small components like clamps and bolts and brackets often dictate entire system's performance. Human installation errors were mainly responsible for many of the failures that could have been prevented. To conclude, overall, mechanically attached systems perform better than ballasted systems. Roof edge placement was a major contributor to failures, and workmanship errors were widespread. Updated codes, improved testing standards, and better racking designs are already addressing these issues. Future success depends on site-specific engineering, improved training, and thorough inspection practices.